Good morning, everyone. Let us discuss today the factors affecting the magnitude of crystal field stabilization energy (CFSE). This crystal field stabilization energy also can called as crystal field splitting energy. Okay. Initially, let us know the definition of crystal field stabilization energy. In a complex after the d orbital splitting, after the splitting of valency orbitals, the energy gap from lower energy state to higher energy state called as crystal field stabilization energy. CFSE. This is known to you. Once again, I am repeating the definition. When the complexes had gone through with the ligand effect, valency orbitals going to be splits into lower energy level and higher energy level. There, the energy gap between lower energy state to higher energy state is known as crystal field stabilization energy. This crystal field stabilization energy can be affected by the metal factors, ligand factors, and geometry factor. When we are going to change the metal ion, the CFSE will going to change. When we are replacing the ligand in a complex, that also will affect the crystal field stabilization energy of the complex. And when we have different geometry complexes in comparison, the geometry when it is changed from one complex to other complex also will be have different in crystal field stabilization energy value. So let us discuss the metal side factors initially. Nature of metal ion. In this title, we will be going to have different metal replacements. We will going to have different metal oxidation states and different electron density metal ions we will going to take, and with this replacement from one to other, how the crystal phase stabilization energy going to be changed we will be observed here, right? So initially, that the first same metal with difference in oxidation state. When we take the same metal ions, different oxidation state metal ions when we take, and when we change the metal ion from one to other, right, what going to be happens in crystal field stabilization energy we have to observe. Let us take that, right, same metal we will going to have here iron, and iron we know that its stable oxidation states are +2 and +3. Here that +2 +3 oxidation state iron when we take, and when we choose a similar complex hexaquo iron 2 complex and hexaquo iron 3 complex, ferrous complex, ferric complex, aquo ferrous complex, aquo ferric complex, when we take octahedral complex, the CFSE of these two when we calculate here the CFSE is increased from lower oxidation state to higher oxidation state. Hexaquoferrous complex CFSE is lower than hexaquoferric complex CFSE. This is what we observe in practically. So the statement will come like this. Same metal with different oxidation state. Metal complexes CFSE will increases with increase in charge on metal ion. Yeah, that is what observed, na? Right? Here to here, octahedral complex, ligand sets aqueous, right? And metal is iron and iron. Where the change we observed here the change is same, simple and oxidation state of the metal ion. Here we have the ferrous metal ion. Here we have ferric metal ion, right? Ferric metal ion. With the simple change on oxidation state of same metal complex, it has the increased CFSE in high oxidation metal complex than low oxidation metal complex, which is nothing but when the oxidation state increases, the CFSE will be increases, right? The reason what we can explain here is, as the charge on the metal ion increase, right? So +2 to +3 in iron, right? The +3, the positive charge on iron, right? 3 is showing that +3 is showing that 3 electron deficient, wherein ferrous complex +2 in oxidation state will shows that its oxidation state of +2 indicates that the 2 electron deficiency on ferrous complex, right? So from ferrous to ferric, what happening, as a charge is difference, as the charge is +2 to +3 increases from ferrous to ferric complex, the deficiency, the electron deficiency on metal ion also will increases, right? So when the metal ion charge is increasing and deficiency of electron is increases, right? What happens, the bonding capacity or attracting metal ion to attract the electron density from the ligand side will going to increase, right? Whichever will be the very deficient in electron, that can be grab electron density very effectively, isn't it, right? It is simple as that. If the two persons are hungry, if the two same persons are in hungry, right, one is more hunger than the second person, right, then what happens, whoever the more hunger person, he can eat more food, right? Same similarly, as here the iron +3 ferric metal complex having +3 oxidation state, more electron deficiency will attract the electron density from the ligand side effectively, right? So when it is attract the electron deficiency in more extent, what happens, it forms the metal to ligand bond stronger and shorter, right? Shorter stronger bond is formed by the ferric complex than the ferrous, where the ferrous is +2 electron in oxidation state and only 2 electron deficient. So what happens, it can be weakerly attract the electron density from the aqueous ligand sites when compared to with the ferric. So far the weaker bond it can be observed in the ferrous complex and stronger bond is observed in the ferric complex. That is the one, right, with respect of electron deficiency, right? The other point is, as a charge on metal ion increases, what happens, charge when it increases, the size will be synchronized, right? The size will be become smaller, right? When the charge increases, the nuclear effect will be more onto the nuclear effect onto the valence electrons will be more. When there is a more nuclear effect onto the valence electron, they can synchronizes, right? When they synchronizes, the charge of the size of the metal ion will be shorter, right? When shorter metal ion, right, when getting into the bonding, the bond length will be becomes shorter, right? The bond length is defined as what? The distance between two elements in a bond will be known as bond length, right? When there are two elements are in bonding, the distance, nuclear distance from one nucleus to other nucleus will be known as bond length, right? When there is an atom size is getting decreased, what happens? The bond length will be get decreases, right? Here again, when there is a bond is decreasing, what happens? Stronger shorter bond will forms. With this stronger shorter bond, the ligands will be more effectively interacts with the, right, gets closer to the metal atom. When it gets, the ligands are getting closer to the metal ion, right, and its metal ion's valence electron density, right, what happens? The repulsive interactions between metal valence electron to ligand negative charge will be going to increase, right? The ligand's negative charge effectively, when the size is shorter, the bond lengths are shorter, the negative effect of the ligand side on valency metal ions will be going to increase, right? When they are getting closer in interaction, that is happens into the charge increased metal complexes, right? So when this happens, what happens? The splitting will be more extent, right? When there is an repulsions going to more increase, what happens? They go away. The whatever the sites, whatever the orbitals are affected more effectively, right, that will go reaches to the higher energy level, which is lesser in effect, that will gets into a lower energy. The energy gap will be created into more extent, right? With this, when there is an energy gap between lower energy to higher energy is increasing in high charged metal complexes, that is nothing but what? Increase in the CFSE. The CFSE, how we defined it? The energy gap between lower energy to higher energy states, right? The lower energy state higher energy to higher energy states energy, whatever the energy gap it is there, that is CFSE. Here the gap is here creating more in the charge increase, right? So that's how the charge increase will makes the CFSE to increase, right? That the statement here I will give. As the high charge on metal ion indicates more electron deficient. So so that the metal ion forms stronger and shorter metal to ligand bonds, right? That is the one. And the charge increase, will decreases the size of metal ion, right? This all affect the metal with high charge will form stronger and shorter metal to ligand bond. Will forms stronger shorter metal to ligand bond. Stronger metal to ligand bond forms. This stronger and shorter bond will facilitate ligands to approach metal valency electrons more effectively. So that the valency orbitals destabilizes more and splits into high energy gap. So the crystal field stabilization energy will increases with increase in charge on metal ion. Is it that? That is what we have explained now. So that is one of the metal factor, right? We can quote here. The second thing is, let us take the different metal ion with different charge. Initially we gone through with same metal ion with different charge. Now let us take the different metal with different charge. Such as vanadium chromium complex. Let us discuss hexaquo vanadium 2, hexaquo chromium 3. Let us take this right here. The same structural complex, ligand is same, where the metal is changed and the charge of metal also is changed, right? In this scenario, again the CFSE of these two complexes, when we observe, same result of first statement is there, right? Statement is even in different metal with different charge will have increase in crystal field stabilization energy with increase in charge on metal ion. Right. What is the statement? As even the metal ions are different, right? As when there is a charge is increases, the CFSE is increased, right? So what is the common things here we observe is the metal, the ligand site is same, the geometry is same, right? The metal sites are different and their charges are different, right? When in this situation, even there is a different metal when we take, what happens here, it is the electron density from one metal to other metal also going to be uh, same here, right? Vanadium plus 2, scandium, titanium, vanadium, nothing but it has the D3 electron density, 3D3 in vanadium plus 2 oxidation state. In chromium plus 3, scandium, titanium, vanadium, chromium, right? It's fourth element. The first transitional series, fourth element, right? Where in the plus 3 oxidation state of chromium, it also will have same electron density. That is what 3D3, right? So the electron density also same, right? So electron density is same even we change the metal ion and their oxidation state, the same electron density metal ion from here to here, right? But increase in oxidation state from here to here, right? What happens there, the sizes from vanadium plus 2 to chromium plus 3 is smaller, right? Chromium plus 3 is very smaller size metal ion, that is the one. And as the charge plus 2 to plus 3 plus positive plus 2 positive 2 to positive 3 is from vanadium to chromium is also going to affect, where plus 3 in chromium is showing that 3 electron deficient, when compared to vanadium it is only 2 electron deficient. So the chromium having more electron deficient, right, and smaller in size compared to the with the vanadium plus 2, smaller size, electron deficient, more electron deficient, will form a stronger shorter bond with the ligand sites, right? So when there is a stronger shorter bond with aqueous ligand sites, right, what happens, the ligands will, the aqueous molecule ligands will be interacts more effectively, more innerly affects interacts with the chromium valence electron density, right? So the 3 electrons of here in chromium affected by the aqueous ligands in more extension, right? Thus 3 electron affected by the aqueous ligands, when there is more effective, the orbitals destabilization will be in higher extent. When there is an orbital destabilization is high, then what happens, the splitting will be more extent, right? The energy gap will be creates into in more, right? So when there is an energy gap is more, nothing but it is the value of CFSE also will be more, right? Same such of first statement reasons, right? That is, let us see the third different factor from the metal side. That is, initially we taken same metal, different charge. Here we taken different metal with different charge. Let us take the same metal, sorry, different metal with the same charge, different metals with same charge, right? Let us consider now different class. Initially we taken iron, there here chromium, cobalt, first side of the transitional series. Next we will go for the second side, right? Later transitional elements when we take let us take cobalt and nickel, right? Cobalt plus 2 and nickel plus 2 let us take. So here why? Because the same charge we have to consider. So hexaquo cobaltous complex, hexaquo nickel plus 2 complex, let us consider this, right? The CFSE of cobaltous complex, the CFSE of nickel plus 2 complex, right? What happened here, it is the practical results shows that the cobaltous complex is more CFSE value, has more CFSE value than nickel. Here there is no discussion of charge now. Till the second point we have gone through with the charge, right? When there is a charge difference, whatever the electron density, whatever the things, right? Even the same electron density or different electron density, right? In the iron case we have the two different right, here also the same oxidation electron density, here also the same oxidation, right? Irrespective of metal ion, right? Whatever the charge is more, right, that ultimately have CFSE is more, right? Here let us consider that the charge is same now, right? The charge factor now ruled out. Then what we can observe here to here, cobaltous to nickel plus 2 is cobaltous, actually it is an 3d7 4s2 element. When has the positive plus 2, it will be 3d7 in electron density. Nickel 3d8 4s2, when it is loses 2 electrons, it has the plus 2 charge, so it is 3d8 now, right? So here the electron density is the factor, right? Size is same, ligand site is same, so far we will go, charge is same, so we have to go for the electron density. So here what is happening in the plus 2 to plus 7, right? The 3d7 to 3d8, here the 3d8 element electron, 8th electron in 3d, right, is in the same 3d, it is included. The change in electron density is slight, only one, right? There is no massive electron density changing from 3d7 to 3d8, right? Not changing, it is just one electron difference, right? When there is a charge is same and electron density increase, will actually decreases the CFSE. Why this has to happen, right? Before that, let us take the statement. The same charged metals complexes with increase in electrons, increase in valency electrons, will decreases the crystal field stabilization energy. Crystal field stabilization energy, right? That is what practically we are observed, right? The reasons, let us see, right? When the electron density is increases, right? So what happens is, right, this you take nucleus, first, second and third, this is cobalt, okay, right? Here 7 electrons, here 8 electrons, right? Third main shell 7 electrons and 8 electrons, right? When 7 electrons in cobalt, 8 electrons in nickel, right, there when the aqueous ligand is interacting, what happens is, as electron density is more in nickel, their electron density on nickel will be very less, right? Even the charge is same, +2 cobalt to nickel, and electron density in nickel 8 electron density, right? Electrons are 8 in nickel in valency. So having more electron density in nickel valency, right, it can be considered as less electron deficient, right? When there is an electron density is less, right, electron deficiency is less in the nickel, what happens? The effective bond or stronger bond cannot be possible here, right? Wherein cobalt, it has only 7, right? The 7 electron valency electrons in the cobalt is comparatively the nickel 8 is less electrons, right? So we can say that electron deficient, right? It is, cobalt is electron deficient in comparative with nickel 8 electrons, right? So what happens? As less electron density on cobalt, right, it can forms the stronger bond with the approaching aqueous ligand sites, right? When it is formed stronger bond cobalt, right, there it will have splitting capacity is more. When there is an here in nickel having more electron density in valency, 8 electrons in the valency, it cannot forms a stronger bond with the approaching aqueous site, right? The high electron density also will creates repulsive interaction with the approaching ligand site. Thus repulsive interaction will deviates the stronger bonding and forms this weaker bond, and its deficiency, electron deficiency is low comparatively with the cobalt. So for that factor also will nickel to form weaker bond and lengthen bond, right, longer bond. The weaker and longer bond in nickel, what happens, right, the ligand cannot go that extension to the valence electrons to destabilize more extent. So when it is not approaching the effective mannerly to the nickel valence electron, the destabilization of valency nickel orbitals will be less effective. So when there is a destabilization is less effectively happening, there the splitting will be gets lower, right? The splitting will become lower effect, right? The energy gap will be certainly will become low, right? That is what happens into the nickel, right? So here what happens, not only nickel, when there is an electron density is more, same charged metal ions within same complexes, when they form same geometry, same charged metal complexes, even they are different metals, right? When there is an electron density is more, right, it forms the lesser, it have the decrease in the CFSE value, it has a lower splitting capacity, right? That is what the uh, statement we can give here, right? The reason we here we can quote that the nickel +2 has d8 electrons less electron deficient form weaker and longer bond with aqueous ligands. So that the ligands cannot approach effectively towards valency d orbitals and less effectively destabilizes the orbitals. So the energy gap from lower energy state to higher energy state is less, that is less CFSE value. Right, that's how the third metal side factor. Let us come for the last fourth factor from metal side. Right, let us take same charged metal ion with increase in principal quantum number. Same charged metal ions with increase in principal quantum number. Principal quantum number. Right. A group of D metal ions here we have to consider. Consider cobalt, rhodium, iridium, hexaquo, cobalt plus 3 complex, rhodium, hexaquo, rhodium plus 3 complex, and iridium, hexaquo, iridium plus 3 complex. Right. In this, what we can observe is the CFSE from cobalt to rhodium about 40 to 40% increase, and rhodium to iridium about 20%, 20 to 30% increase in CFSE is observed. Right, practically this is what happened. Right, so it's nothing but in the same oxidation state metal ions with increase in the principal quantum number, valency principal quantum number, it increases the right CFSE value in more extent. Right, the statement will be in same charged metal ions with increase in principal quantum number, valency electron density, valency electrons will increases the CFSE value. Right, increase the CFSE, magnitude of CFSE. Right, Why this is happening, right? In the last thing, right, in the last statement, the third effect from the metal side, there also we taken same charged metal ions such as here. Here in this third statement we taken +2 charged metal ions, right? Here in the fourth statement, fourth effect, we have taken that +3 charged, right? Whatever it may be, here 3, here 2, right? All 3, all 2, right? And electron density here, if we come take from here to here, only one electron difference it is taking place, right? 3d7 to 3d8, right? But here when we take cobalt is 3d6 in +3 state, rhodium is 4d6 in the statement, iridium is 5d6 in the +3 oxidation state. In simple, if we take look into the electron density, valency electron density, valence electrons, this is 3d d6, this is d6, this is also d6. Cobalt to iridium, all d6 configurated metal ions only, right? So with that we cannot say that they have all same electron density. Why? Because the principal quantum number, right? In the cobalt it is having a 3d8, in the rhodium it is as 3d6 in the cobalt, in the rhodium 4d6, in iridium 5d6, right? The principal quantum number is changing. With this principal quantum number change, right, the bulk number, right, a, a, a number of electrons change from 3d to 4d, 4d to 5d is more effect, right? More large number of electrons can be changed, right? Here from here to here, what it happens is the valence electrons, when we take, right, 3d10, 4s2, 4p6, after that it is 4d6 actually. So it means that it all totally from here to here 18 electrons are increase, right? Here to here 18 electrons are increasing. Cobalt +3 to rhodium +3, it all 18 electron increase is taking place. From rhodium to iridium, it almost 32 electrons increase will be take place, right? Here 4d10, 5s2, 5p6, after 4d10 4f14 will come, 4f14, 5s2, 5p6 and 5d6, right? When you calculate this, all is 32 electrons, right? So here, as such, in the third statement, the electron change, the electron increase from the cobalt +2 to nickel +2 only one electron, but here in cobalt +3 to rhodium +3, 18 electron difference it is taking place, increase is taking place. Rhodium +3 to iridium +3, 32 electrons increase is taking place with a change in principal quantum number, increase in principal quantum number, right? Where here we can say that a large number, a bulk number of electron density is increasing from the cobalt +3 to iridium +3. This a large bulk number of electron density, when it is increases, what happens is the repulsive interaction with electron density with the ligand sites will be more, becomes increases, right? It is simple that this can be simply, we can say as that in generally, when there are two groups are in quarreling, right? If the group numbers are only 6, two sides, both the sides, the number of quarreling persons are 6, what happens? The quarreling will be one extent, right? When the number is increasing from 6 to what we can say, 18 plus 6, it is nothing but almost 24, right? 24 side of one side of 6, what happens? As the one of the group numbers are increased, members are increased, what happens? The quarreling extension will be more, right? The fighting will be more, right? Again, in the next case, what you take is 38 members are quarreling with 6 members, right? Then what happens? Again, more number of members are increased in the quarreling group. What happens? The quarreling will be high and high, right? That is what happening here, right? From 3d6 to 4d6, it is increasing 18 electrons, nothing but they are 18 plus 6, 24 electrons are coming into an interaction, right, with the 6 of ligand sites. The quarreling will be the interactions of 6 ligand negative charge, and these number of electrons will be more extended, right? That creates that the magnitude of CFSE will be increases, right? So in the iridium case, when we come, it is 32 plus 6, 38 electrons are getting in interaction with the ligand sites. Then what happens? The quarreling, the interactions will be more effective, right? So far, gradual, right, the higher gradual increase is taking place from the cobalt to iridium, rhodium to iridium, right? Almost it is becoming double from cobalt to rhodium, and rhodium to iridium, it is becoming, right, sorry, 50% is increased from the cobalt to rhodium. Rhodium to iridium, it is 20 to 30% is increase, it is taken place, right? So bulk number of electrons increase from the cobalt to iridium will increases the CFSE in very higher extent, right? That is what happens in the fourth statement, right? So here I close the 2-day session of class, right? Hope this video will help you in learning the uh, effect of metal side factors in increase or decrease of magnitude of CFSE, right? So let us close here. Next, by discuss the ligand factors and geometry factors, right? Thank you.